Raw crude oil is a viscous, dark sludge pulled directly from the earth. To become motor gasoline, these hydrocarbons must undergo a total architectural transformation to meet a set of precise industrial specifications. Refining at this scale is more than just boiling oil. It is an exercise in molecular sorting. Every stream within the plant is a response to the specific chemical geometry of the molecules being processed. Two primary metrics dictate a hydrocarbon's value. The first is its carbon number, which is the total count of carbon atoms in a single molecule. This number determines the boiling point and whether the fuel exists as a gas, a liquid, or a solid. The second metric is the hydrogen-to-carbon ratio, plotted on our y-axis. This coordinate system maps every molecule by its size and saturation. High hydrogen-to-carbon ratios with low carbon numbers form high-value gasoline. Molecules settling in the lower right, low hydrogen, high carbon, are rejected as low-value residue or refinery coke. By following the chemical assay of the crude, we can deduce the necessary physical layout of the refinery, building the plant from first principles. Before processing, we characterize the crude using Sarah analysis, dividing the oil into 4 chemical groups: saturates, aromatics, resins, and asphaltenes. This reveals the discrepancy between simple, straight-chain saturates and asphaltenes, the massive multi-ring clusters dominating the heaviest portions of the oil. Crude also contains hidden heteroatoms, specifically sulfur, nitrogen, and oxygen. Sulfur is often structurally integrated into the molecules themselves, as seen in thiophene. This makes the impurity impossible to remove through simple physical filtering. If these heteroatoms and trace metals like vanadium are not removed, they act as catalyst poisons, permanently deactivating materials needed for downstream chemical conversion. To manage these chemical constraints, we must first use thermodynamics to sort the crude by molecule size. The process begins at the crude distillation unit, or CDU. This is the primary physical gateway, where the bulk of the oil is vaporized and separated. The crude passes through a fired heater that must bring the temperature to exactly 398 degrees Celsius. This is a hard thermal limit. If the oil exceeds this temperature, the molecules will thermally crack inside the pipes, depositing solid carbon that clogs the system. Inside the distillation tower, the vaporized crude rises through a series of perforated trays and bubble caps. Steam is injected at the bottom to lower the vapor pressure within the column, allowing the hydrocarbons to rise more freely through the cooler liquid on each tray. As vapors rise, they cool and condense back into liquids precisely at the levels that match their specific boiling points. These condensed fractions are drawn off as side cuts, yielding the primary building blocks: naphtha, kerosene, and gas oils. To control the temperature profile, a portion of the top product is returned to the tower as reflux. This liquid flow ensures a sharper separation between the different cuts. The CDU successfully sorts the mixture by size, without breaking any chemical bonds. However, the residue left at the bottom of the tower still contains valuable heavy gas oils that cannot boil at atmospheric pressure without cracking. To recover these, we route the residue into the vacuum distillation unit, or VDU. By using vacuum pumps to pull the pressure down to roughly 5 kilopascals, we can lower the boiling points of these heavy molecules. This allows us to vaporize the remaining gas oils at lower temperatures, avoiding the solid carbon deposits that would occur at higher heat. Because of the low pressure, the VDU requires a larger diameter and internal packing rather than trays to facilitate the vapor flow. This recovers the vacuum gas oil, or VGO, leaving only the heaviest vacuum residue for asphalt production. Even with these fractions separated, they do not yet meet modern octane or environmental standards. On our plot, we can see that our straight-run naphtha and VGO sit outside the necessary specifications for modern engines. To correct this, we must break long carbon chains to reach the diesel range and branch straight chains to increase the octane. This phase is handled by chemical conversion units such as the fluid catalytic cracker, or FCC. The FCC utilizes zeolite catalysts to crack heavy VGO chains into high-value gasoline and olefins. Simultaneously, straight-run naphtha routes into the catalytic reforming unit. Here, platinum-based catalysts restructure simple chains into high-octane aromatic rings, such as toluene and xylene. To handle the sulfur identified in our initial assay, we utilize hydrotreating units.
These units use high-pressure hydrogen to strip sulfur and nitrogen atoms from the intermediate streams, protecting the environment and our catalysts. While distillation sorts the oil by size, these conversion units rebuild the molecular architecture to create custom-engineered fuels. A modern refinery operates as a massive, continuous thermodynamic circuit. Every transmuted stream from the distillation and conversion units must converge at the blending stations to meet specific market demands. This entire operation requires a constant, real-time mass balance to ensure that feedstock input equals product output across every unit. Managing these concurrent chemical processes requires high-fidelity monitoring. Every pressure and flow rate is adjusted to maintain the stability of the molecular reactions. The architecture is constantly evolving. New environmental mandates, such as those for ultra-low sulfur fuels, force the addition of more advanced hydroprocessing tech. Modern refineries are also adapting to process increasingly heavy crudes that enter the system with very low hydrogen-to-carbon ratios. Ultimately, refining is a system designed to extract precise, high-value order from the most chaotic hydrocarbon mixtures found in nature.